Hello, we are going to discuss about electric field lines now. Electric field lines. This concept was first introduced by Michael Faraday. What is electric field line? Now further we have to understand electric line of force. So electric line of force imagine an electric field. In an electric field, if I keep, so let's say this is an electric field. In this electric field, I am keeping a small positive charge. Now this small positive charge would move in a certain direction. So it might trace a curve. Now that curve along which this positive charge would tend to move, when it is free to do so, when it is not constrained by anything, now that is called electric line of force, which is, if I write, the curve along which a small positive charge would move in an electric field. So this is the idea. So we spoke about a curve. Now let's imagine a curve like this. Oops. So now let's say this is the kind of curve. In this curve, if this curve represents an electric line of force, the tangent in this curve at every point shows the direction of the electric field. Now let's take three different points in this curve. This is point P, say point Q, and this is point R. Now the tangent, the tangent did not come properly. Now let's see. Okay, the tangent of the electric field, that the tangents to this curve at this point, they represent the direction of electric field. This is imaginary. These curves are imaginary, they are not real, but they do represent real field. So the curves are imaginary but represent real field. And another point which you want to know is this is a space curve. Now what is a space curve? It exists in 3 dimensions. Okay, X, Y, Z. So 3 dimensions. That is a space curve. Now we could go ahead and read about some properties of these lines of force. Okay. Let's read about some properties of lines of force. The first one is these curves are continuous, smooth curves without any breaks. Then they always start at positive and end at negative. Another thing is the tangent gives the direction of electric field. They are normal to the surface of the conductor on which the charges are in equilibrium. Okay, so these are some important properties of this electric lines of force. Then there are a couple of other properties very important. Now let's look at this. Imagine this is an electric line of force. In the now this flows from positive to negative, right? In the longitudinal direction, that means in this direction, it tends to contract. So it is trying to become smaller and smaller, because we know we have a positive on one side and the negative on the other side. So it is trying to contract so that it creates, which indeed results in attraction. So we know the opposite charges, they attract because of this. Along the longitudinal direction, there is a contraction happening. Now let's see, there are two different lines of force. This is going from positive to negative. There are multiple lines of force like this. Laterally, that means sideways, it is trying to expand. So expand laterally. Now when it expands laterally, it causes repulsion. So now we know how the repulsion and attraction are caused in an electric field. And then when we speak about the electric field, the spacing on an electric field could tell us some things. Now let's say the spacing is very close, that actually represents a very strong field. If the spacing is farther, then they represent a weak field. However, if the spacing is parallel, then we are speaking about an uniform field. That's what the spacing of the electric lines of force tell us. Now let's see how the electric lines of force would be like for a positive charge. So I am keeping a positive charge at the center, and we told that the lines would be going away from the positive charge like this. So this is how the electric field lines would be for a positive charge. So it has lines like this, and we have to mark it as going away. This is for a positive field. Now let me do this for a negative charge. So this is a negative charge. At the center we have a negative charge. So here the charges don't go away, they converge towards the center, they come towards the center, the charge itself. So here we will show it differently. So it is going to come towards the charge like this. So positive charge, it's outwards, and it is spherically symmetric. If you don't know what spherically symmetric is, in a moment I will explain. So in a negative charge, it is inwards. Now I use this word spherically symmetric. That means symmetry is in all the directions. if you take a sphere, it is, you could cut this in all the directions, it is symmetrical. However, if you take the case of a cylinder, it is symmetrical only in one direction, so that is called cylindrical symmetry. If you cut this cylinder at any other point or any other way, it will not, the resulting pieces would not be symmetrical. So there is only one axis along which you could cut. So that is the difference between cylindrical symmetry and spherical symmetry. There is a positive charge here and then there is a negative charge here. How the electric lines of force would look like? It is going to look like this. So the lines are going to bend like this. This is how it is. And everywhere it is starting at the positive charge and going to the negative charge. They go from positive to negative. That is the first observation you can make. Second, they contract lengthwise. That means they are trying to come closer together and they are cylindrically symmetric. They are cylindrically symmetric. This is what we can tell about two equal and opposite point charges. Equal and opposite. Point charges. Now what happens if there are two equal and not opposite, same point charges? Let me go for two positive charge. This is a positive charge, this is a negative charge, right? So they try to act like this. They get repelled. So this is positive. Both are positive. They get repelled like this. So there is a lateral pressure that is causing the spacing to increase. So they get pushed away as a result. And then even in this case it is cylindrically symmetric. Cylindrically symmetric. Now in this case we have this point. Now if I call this point as N, now this is a point where the electric field is 0. Now that point is called neutral point. What happens in the case of a positively charged conductor? Let's say there is a conductor which is positively charged. So let's visualize a conductor like this. So it is positively charged. It is positively charged. So we are going to have the field lines like this. We have some field lines going away in this direction and some again going away in this direction. So we are going to have parallel lines of force. Then they are going to be equispaced, equal space from one another. Very important point here is the density of the lines. Density of the lines is how close they are together. That is directly proportional to the electric field. That is an important result we would want to remember. Density of lines is directly proportional to the electric field. Now how can we solve this? Now let's say there is an electric field. It goes like this. Now this electric field density of the lines, if you could see the density of the lines here, it is high. Now let's say I imagine a surface in this part, and then there is a surface in this part. There are two different surfaces. So the electric field at the green surface is also high. As we move, the electric field goes down, becomes lower, and the density also goes down. That also becomes lower. So that is a key observation which we would want to remember.